Hi, my name is Sharmeen Kiani. I will be your instructor for this lesson. You must be here to either learn about atomicity and durability or refresh what you already know. So without a further ado, let's dive into it. Everything starts off with the use of a database to store information, which is required by real-life applications such as banking, healthcare, finance, and many more. Everywhere you look, there is a need for a database. Take, for example, the bank where you keep your money. The money is in fact stored in databases. Now, to protect data and keep it consistent, transactions are used, where a transaction ensures that even in the case of failure, data remains in the previous state as it was at the start of the transaction. Wait, here I am talking about transactions without giving you a generalized idea of what a transaction really is. So, let's rewind back. I want you to think of a transaction as a sequence of operations performed as a single logical unit of work. You withdrawing money from your bank account is an example of a transaction that has occurred in its entirety, from start to finish. So make sure you understand this completely, that in fact, a basic operating system, it is not possible to have a partially completed transaction. So either a transaction executes or it simply doesn't. You must be wondering at this moment, why and how do we ensure that a transaction in fact does happen from start to finish? Well, if we want to keep our database consistent, then we have to focus on the transactions that act on the database. If these transactions are correct and consistent, then the database will be correct as well. You could say it is similar to a domino effect, where one affects the other. So if a transaction is working well, the database will work well. But if the transaction is experiencing faults, if it's inconsistent, then obviously the database won't work properly and will remain inconsistent as well. Now that we understand what a database is, what a transaction is, and for everything to work or run smoothly, the transaction needs to work well. So that brings me to the second part of the question. How do we ensure that a transaction works properly? Well, by using the asset properties. It is stated that if transactions use asset properties, then it is guaranteed that the database, which have those transactions working on it, will remain consistent. The asset properties each signify a piece of a puzzle, where together they work, or rather ensure that transactions work well. A stands for atomicity, which requires that each transaction is all or nothing. If one part of the transaction fails, the entire transaction fails, and the database state is left unchanged. C stands for consistency, which ensures that only valid data following all rules and constraints is written into the database. When a transaction results in invalid data, the database reverts to its previous state, which follows all customary rules and constraints. I stands for isolation, which ensures that a transaction appears as though it is being executed in isolation from other transactions, even though many transactions are executing concurrently, or rather side by side. D stands for durability, or the way I remember it as permanency, where the changes applied to the database by a committed transaction must persist in the database. These changes must not be lost because of any software or hardware failure. While I was researching, I found this extra piece of handy information where a database management system that supports all four of these properties is said to be asset compliant. The asset properties that we will be focusing on this video will be atomicity and durability, that are controlled by the recovery manager in the database management system architecture. Let's now look at an example where atomicity would be put into practice. Remember, atomicity ensures that either all of the operations of a transaction are reflected in a database or none are. Let's take an example of a banking system to understand this. Suppose account A has a current balance of $400 and account B has a current balance of $700. Account A is transferring $100 to account B. This transaction has two operations acting on it: debiting $100 from account's A balance and creating or rather adding that balance to account B's balance. If both operations were to succeed, our expected results would look like the following, where account A would have $300 and account B would have $800. However, in this case, the first operation passed successfully, while the second one failed. In this case, account A's balance would be $300, while account B's balance would be $700 instead of $800. This is unacceptable in a banking system. Either the transaction should fail without executing any of the operations, or it should process both operations. The atomicity property ensures this. Now, if the two operations had been successfully performed as a whole unit, then the transaction would have been committed. This would have been ensured with the SQL commit statement at the end of the transaction. Commit is a way of saying the transaction has been correctly completed, so go ahead and save. However, in this case, when the second operation did not go through, or rather was lost, it would be the responsibility of Atomicity in a database to roll back any changes that may have been made. So any previous alterations, such as $100 being deducted from account A, would be all reverted, bringing the database back into its previous consistent state, as you can see, where account A has $400 as it had previously before any changes were made, and account B has $700. Now let's look at the asset property durability. Durability in a database is a property that ensures that transactions are saved permanently and do not accidentally disappear or get erased, even during a database crash. This is usually achieved by saving transactions to a non-volatile storage medium. Let's put this logic to the same example we used to explain atomicity. Say the previous process repeats itself where the first operation runs successfully and $100 is deducted from account A, but suddenly a database crash occurs before operation 2 can begin and $100 cannot be added to account B. The durability property should bring the database back to its last consistent state before any uncommitted changes occurred. This would be before operation 1 began. So, where account A had $100 deducted from it, all changes would be reverted and account A would have that $100 back into its account. So, to reinforce, once a user issues a commit command, then the transaction is first written to the database files stored on a non-volatile medium such as a hard disk, which is done before confirming to the user that the save has occurred. If a database crashes before the save, the data is still on the transaction's logs. The next time, the database is restored, but any uncommitted changes are undone or roll back. Now, to end things properly, let's do a quick quiz to ensure that everything you have watched and learned in this tutorial is in fact understood by you. Read through the first question and think of what the answer could be. I will give you 5 seconds. Done? Good. It's durability. Hopefully you got that right. Now I'll give you another 5 seconds to read the second question and think about what the answer could be. Done? Good. The answer is atomicity. Hopefully you also got that right as well. Well, that's it for today, folks. Thank you for watching and I hope you learned.